All right, welcome everybody to week 9, day 2. We're going to be talking about pointers today, which is, we've sort of seen a little bit of them before without knowing about it. Pointers are when you work with the RAM address, the address in memory of a variable. Normally we sort of ignore it, but as you'll see for your homework assignment, which has been pushed out already, you kind of need to know it to do the assignment. So, let's go over your homework assignment first, and then we'll go over the knowledge later. So your homework assignment, your homework assignment is in Bridges, Mountains, 40, and it's kind of fun. It's kind of a fun assignment. What it is it'll bring together everything that we've done so far. It starts off by loading a giant 2D array of data. This is a 63 by 43 array, and you can see there's, I think it's 63 rows. Let's see, how many rows? 50. So it's 40 rows that are 63 wide, whatever. It's a 63 by 48 array, and I think this maybe columns, and that's rows. And it loads all of this data into memory. What this data is, it's actually elevation data taken from the US government's website, where you could select a chunk of America or the world really, and it would give you the elevation data. This is on a about a kilometer scale grid, and these are heights in meters, I believe. And so what your assignment is going to be is you're going to load this 2D data into memory, and you're going to find a path from one side of the map to the other. It's going to look something like this. So this is a map taken from Colorado, and the white dots on there are high elevations, the darker is low, and the path is going to be this purple line here, where you are going to travel. And the rule is this. So for the assignment, you're going to start off by loading a giant 2D chunk of GIS data, Geographical Information Systems data, which is provided to you. You don't need to generate this, which is good because the US government's tool doesn't work anymore. They actually broke it and basically took this exporting feature offline, which is a shame. I mailed them and they're like, "Nah, we're not gonna fix it." So good thing that I downloaded the data when I did. Let's put it that way. So first step is the program is going to load a giant 2D array, and it's just a 2D array of integers, as is normal for these sorts of things. We use integers all the time. Then the user is going to type in a row. So in this case, the starting row is 100. And then if we zoom in, let's see if we can zoom in here really far, what you'll see is that the path here is following the valleys and things like that, like especially like right here in the map. Because the rule is this: for as you walk, you're going to walk from the left side of the map to the right side of the map. Every time you take a step to the right, there's only 3 possibilities for where you step: going east, going northeast, going southeast. And so you're always going to go east, but your row is either going to stay the same, or it'll go up a row, or it'll go down a row. Okay? And up a row is actually down a row, because row 0 is the top row of the array. So as it goes along, it's going to pick between the 3 options. Here you can see it's moving northeast, here it's moving southeast, and here it's moving east. And the spot you're going to choose to move to is the one whose elevation is the closest to your own. So if I'm at elevation 100, and to the right is elevation 100, and northeast is elevation 200, and southeast is elevation 300, I move to the east because 100 is closer to me than 200 and 300. So you subtract the difference in elevation of the 3 options, east, northeast, southeast, and whichever one has the minimal difference in elevation, that's the spot that you move to, and then you repeat. And you repeat until you hit the right edge of the map. That's the algorithm. You're going to be navigating through a 2D array, basically. Now, there's some bounds checking you need to do. So where do you think you might run out of bounds when you're doing this? What do you think? What scenario could occur that will cause the path to go out of bounds? Can you think of? If they're equal, I think you flip a coin or something. Is the rule. Equal elevation is not too common, but it does happen, and you can actually get a different result depending on it. What if you run off the top of the map? Yeah, exactly. And so let's say that we just kept going northeast, 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 and we hit row 0. When you're on row 0, if you grab the value northeast of you, you're going off the bounds. And so you're gonna want to be sure that you're not going, if you're not going to grab data off the edge of the map this way or off the edge of the map that way. So if you're ever on the top row or the bottom row, there's only 2 options to move. So if you're on the top row, you can move east or southeast. If you're on the bottom row, you can move east or northeast. So there's a little bit of bounds checking logic there. Also, what if the user enters, I want to start on row 9 million, or I want to start on row -5. So you're going to have to do a little bounds checking in there to make sure your code doesn't crash and stuff. But yeah, so this is using a website called Bridges, and Bridges is a really cool website. I've been working with the people there in University of North Carolina for a few years now, and they're really good people. And what they want to do is make it possible for students to visualize their code, what their code is doing. So for this assignment, rather than, I don't know, just getting a bunch of text, and it's really hard to see. Like if you're looking at this, like, you know what I mean? Like, oh yeah, clearly, all right, clearly, northeast of me is this one, and east is that one, southeast is that one. Maybe, I don't know, I'm not really counting. So clearly southeast is the correct. It's really hard to like, you know what I mean? Like wrap your brain around just a giant wall of numbers like this. You know what I'm saying? And so by visualizing it, you can actually take a look at the world. It's pretty. And then you can see if your route is going to like follow. Like if there's a canyon like this, your route will tend to follow the canyon because, it's cheaper. Like it's going to be more level for you to stay on the valley floor than it is to go up a mountainside. So you can sort of eyeball these things and see if your code is working as expected by visualizing it. So in order to zoom back out, in order to use Bridges, what you're going to do is go to their website, which is bridges.github.io. Here. Nope. Delete one more letter. There we go. And paste that into Discord. It's in the instructions as well. So what you're going to do is you're going to go to that website, and there is a link. Let me move it below my face, which is blocking it. Right here to log in. So you're going to click on login, and then you're going to click on sign up. And what that's going to give you when you click on the profile is it's going to give you a username, and it's going to give you a API key. The API key is going to be like a password kind of that you're going to use for your projects. And every project you create on there will have a project ID. For example, here is Colorado starting on row 100. This is project ID 900. And then if I have Colorado starting on row 150, this is project ID 901. And so you can either do all of your stuff in here on starting on road 200 for Colorado 2. This is like over towards Denver, I believe. Sorry, and this is the same one. So I probably should delete the other one, huh? It should be the same. It's row 100. But this is a different project ID, so I'll delete this one. And then you can see what it would look like in CSI 26 because you do this assignment again in CSI 26. Okay? And for CSI 26, it's not just going from the left edge of the map to the right edge of the map, but you actually have to navigate from any arbitrary point on the map to any arbitrary point on the map using the powers of discrete math. CSI 26 teaches you algorithms and advanced mathematics, it's not really advanced, that will allow you to do things like this. And it'll give you better programming skills as well. So my CSI 26 people are literally doing the same assignment that you are right now. They're just doing a harder version of it. So, yeah, pigeonhole principle. Is this how GPS works? Like you mean like Google Maps, like for navigation, things like that? Not your assignment. For the CSI 26 assignment, yeah. So this code here doesn't use roads or anything, so this is just using elevation data. And what is happening for this assignment is that vertical changes are penalized at a factor of 20. So if there's 100 meters of elevation gain, that's considered the same as 2,000 meters of horizontal distance traveled. So what it's trying to do is minimize the total distance traveled. And by doing so, it tries to stay at the same elevation as much as it can. But there's no roads on here, right? So this is like Lake Isabella or something like that down in Bakersfield. For the GPS navigation on your cell phone, Google, because who uses anything else, has road information. And so it's doing the same, it's the same algorithm, kind of, but it's using road information, whereas this is using road data, whereas we're using elevation data. And so I grabbed from the government elevation data for a lot of different parts of the world, like Victoria in Africa. This is the Korean Peninsula, obviously. You got China and Japan, and you got North Korea and South Korea over here. And I added in false coloring to it so it looks nice, I guess. And so if you're going to navigate from North Korea to South Korea, you're going to go this way, which explains a lot about the Korean War, by the way, and why it progressed the way that it did, and why the demilitarized zone is so heavily mined, because Seoul is right on the marching path of any army coming in from North Korea. So Seoul is like around here, right? And if you look at the mountains, like if an army comes through, they're going to come through Seoul and they're going to pulverize it. They're really close to the North Korean border. So like when you look at this kind of stuff, it actually kind of explains like, you know, politics and stuff like that too. Dijkstra's much fun. Yeah, Dijkstra's algorithm is shortest paths. And there's also A star, which is used and some other stuff. So anyhow, oh yeah, and then there's this too. So Bridges has the ability to grab street data out of OpenStreetMaps. And you might recognize the road network here. Anyone take a gamble as to what 2 points are being navigated between here? This is Fresno. Anyone recognize the roads? City to community. That's, I don't think that's city. That's community. That's Clovis Community College. So yeah, good. That's the Chick-fil-A. Let's see, Chick-fil-A is off Friant, right? Friant. So which would be right here. So that's the 41. That's Friant. So Chick-fil-A is going to be around this intersection over here. I think this is Fresno, and that's First. So that's like First and Herndon or something like that. And then, so it's navigating from there to Columbus Community College. Chili's, yeah. Yeah, it's supposed to be Chili's. Okay. Yeah, and so there's a lot of really cool stuff you can do with Bridges. Okay. Bridges does have documentation. You shouldn't need to tap into it for this assignment. You can watch a video on how Bridges works, and you can click on some of the their examples, and it will launch a visualizer. What's going on here? I don't know what happened. Anyway, you don't really need to mess around with that too much. Everything you need to know is in the assignment. The main thing is you're going to need to go to login, create an account, get a username, and API key. That's the main thing. Because when you do this assignment, first thing you're going to do is need to type in your project ID, which could be any integer you want. 1, 1001, it doesn't matter. It's just every time you update it, that project gets overridden. So just pick one and stick with it for the assignment. And if you do another assignment, pick a different project, and then it won't overwrite itself. You're going to type in your username there, and you're going to type in your API key there. The API key is like a password. So when you create your account, it generates an API key for you, and you can click on a button and it'll make a new API key. So if, for example, you did what I did, which is yesterday reveal to YouTube my API key. As soon as class is over, I hit make new API key, which invalidates all the old ones. They don't work anymore. And you essentially get a new password. So this code here needs you to fill in the gaps. You're going to need to punch in this, and then delete this line. And I have this thing does not compile by default, and I do that for a reason. Because you can try running the code without typing in a username and API key, and it's just not going to work. So I put this in here to like sort of force you to pay attention. You need to register, you need to get a username and API key, punch it in, and then once you punch it in, delete this line. So static assert is like the assert function, except it runs at compile time. So this code will not compile because we're static asserting false. So yeah, it just won't compile. So once you get your username and password, or not password, API key in, delete that. You're good to go. Okay. And then this thing here makes sure that you're compiling the project with make. So for this project, you're going to use make to compile. You're not going to use G++ for compile. You're going to type make to compile it. If you don't, it will not compile. So make sure you type make. If you don't, then it'll print this error message for you. Okay, so let's go through the sample code that's given here, and we'll talk about why we're learning pointers today. Pointers and arrays, C-style arrays, go together like peanut butter and jelly. And I told you perhaps that I don't use them very much anymore in my personal coding, but a lot of people use them. And guess what? This code here, I didn't write it. You know, this is real code from the people who made the assignment. And they use, you know, and there's nothing wrong with it, like intrinsically. Like if you know what you're doing, it's fine. I just prefer vectors these days. And so let me go through the code, and you'll see some syntax in here you won't recognize, and I'll explain it, and also then we'll hop over into like some demo code and like kind of go through how pointers and stuff like that works too. But let's go through your assignment first. So first of all, this thing here is the bridge between your code and the website. So what you do is you create this thing of type bridges called bridges, and you pass in your project ID, you pass in your username, you pass in your API key. And those are these three things up here. And when you do that, that's going to essentially be the part that connects to the website and uploads your data and visualizes it and all that magic. You don't need to worry about that. How to log in, you just toss in your username and API key, and then this thing handles all the rest. How do you do networking? Handles it for you. Okay, so reading input elevation data. So we're going to be reading a 2D array. A 2D array has a width and a height, right? Now, we're storing it in a 1D array, and this is the thing that hurts students' brains. This here is the same thing as if we had written int elev data, like that. Okay, so it's an array. It's a one-dimensional array. So we're storing two-dimensional data into a one-dimensional array, and this is very, very common for various reasons. First of all, when you pass a 2D array to a function, the syntax is terrible, and you basically have to hard code the dimension of the width of the array into the function itself. And you can't just like pass it in. You have to know the size, and it's hard coded into the function prototype itself, which is absolutely garbage. It's absolutely garbage. So we typically just don't use 2D arrays at all. Okay. So this is a 1D array. It's a 1D array that's going to be holding 2 dimensions of data, and we'll go over how the hell that works in a bit. Okay, so notice none of these variables are initialized. That's okay, because we're going to pass them in here by reference, and this function here is going to initialize them for us. This is the file we're going to open. By default, we open Colorado 1. That's our go-to map. But if you run the program, if you type in like a.out space Colorado 2 ... then it will open a different file instead. It then calls this function. This function does the file stream stuff that we were talking about. It opens the file, it reads out the width and the height, and max value is the highest elevation. We use that for the coloring. The highest elevation is going to be white. It's going to be snow-capped peaks. And then we pass in the file name. So we pass in Colorado . Okay, so then this is going to return a pointer. Just this thing. A pointer is an array is a pointer, with one small caveat attached to that. They're basically interchangeable. So it's returning an array. Let's put it that way. And you can think of it, this thing which is called a pointer, it's just an array. It's returning an array of data. So we're holding the array of data here. We then changed the title on the project. By the way, this is a partnered assignment. You can have a partner or two on it. All you guys can be graded separately. So it's not that big a deal. But what is a big deal when you have a partner is you have to go up top and put the name of your partners up here. Okay? Because I run a similarity detector on your assignments that you turn in, and if it turns up that so-and-so is 100% similar to so-and-so, my first reaction is, okay, they're cheating, right? Because it's impossible to have code that is letter for letter the same. And the similarity detector isn't fooled by things like variable names and comments and white space. None of that matters, right? And even if you start moving code around, then the similarity just dips a little bit. So, in general, don't cheat, right? For this assignment, you're going to have a partner. So all you have to do is be like, yo, I partnered with Bob or whatever, right? And then when I see that two people turn in the same assignment, I open up the code to look at it. It's like, oh, I partnered with Bob. Okay. Not a big deal. It's very stressful for students to, be like accused of cheating. So if you don't want to plagiarize, give credit where credit is due. Give credit to your partner. Okay. So, yeah, and it's stressful for me too. I don't like accusing people of cheating either. Okay. So cite your sources. You know what I mean? It's academia stuff. All right, so put down here the last names of all of the people in the group. So this would be like, Kearney and Mincarelli and Corrente, Mountain Path, something like that. Change that. Okay, then the user types in the starting row, right? Like we'll start on row 100, and then we're going to go. So this is the heart of the program here. So find path is the actual algorithm. And what that's going to do, it's going to take a step east every time, but it'll either be east, northeast, or southeast. And it does that until it hits the end of the map. And every time it takes a step somewhere, it sets the elevation to -1. So you actually record your path by carving a hole in the mountain. So you've got this 2D array of data. And what you're actually going to do is you're going to destroy the mountain as you move eastward. You're going to leave the Grand Canyon behind. What you're going to do is you're going to set the elevation to -1 on every step you take. And the reason for that is because we're going to visualize it here. And when we visualize it, you need to mark a colored line where you walked. And so the place where you walked is marked by setting the elevation to -1. Right now, the color is purple coming out of it, and you need to change the color to be blue, which is extremely difficult and complicated. We'll go into that in just a second. And then here's the animate. So this code here takes the color grid. A color grid is a 2D image, RGB image, and visualizes it. So that's it. When it runs, it'll be like success. Your thing is now up on the website. It gives you a URL. You double click it to copy it, go to your browser and paste it, and then you can visualize your thing like I did just now. You can just open up you can log in on Bridges and it'll show you all of your projects. You can click on it, and every time you run the program, you just hit refresh, and it'll come up with a new image. So it's pretty fun. It's a fun assignment. It's really fun to visualize stuff, and it does really help just sort of get an intuitionistic understanding of like if your code's right or not. Because if your code's wrong, like when I was doing it, I had a bug in it, and it always went northeast, and so it always went northeast if there was a tie, which I don't know if is actually a bug or not, but like I put in a flat plane and the thing just went bloop, like that, and I was like, maybe I should just make it go east, because it's just weird looking. Like you hit a tie and it just goes whoop like that. Like just traveling east seems better to me. I don't know, or flip a coin or something. I don't know. Okay, plagiarism.site sources. Yeah. Just put down who your partner is, and it's not a big deal. Okay, so we'll talk about this stuff here. What this delete thing means. We're going to talk about that on Friday. Okay, so here is the functions. And you notice the functions here are below main. If I scroll up to the top, you'll see that main is up top here. And a lot of people like writing code that way. When you're writing procedural code, which is the type of coding we're doing in this class, main is the boss, right? It's the boss. It's the heart and soul of the program. So you start at the top of main, you go to the bottom of main, you're done. Yeah. So a lot of people put main front and center, right? They want it at the very top, so you don't have to hunt around for main. You open up the file, and there it is. All right, let's do this. Okay. But if you want to do that, if you want to have your functions that you call below main, you have to forward declare them. And this is how you do it. You, like if we want to forward declare find path, what I do is I type YY, copy, come up to the top, P to paste, and rather than having an open curly brace there in the code, what you do is you put a semicolon. And that is how you forward declare a function. Okay. You might notice here that the parameter name is different from what was actually in the function. That's fine. Because what you're doing when you're forward declaring something is you're telling C++, you just have a semicolon there, you're just telling C++, hey, there's a function named findPath. You don't know what it does yet, but it exists. Okay? This findPath function returns nothing. It doesn't have any return value at all. And it takes the following parameters. It takes an integer pointer, it takes an integer, it takes an integer, it takes an integer, and an integer. The variable names do absolutely nothing. I can actually delete these here, and the code would be exactly the same. The variable names there are for people to read. They're not there for the compiler. All the compiler needs to know is this. What's the name of the function? What are the parameter types? What's the return type? The reason for this is because C++ is a strongly typed language. And so as we come down here and come down into find path and stuff, if I try doing something like this, see out find path, this won't work. Why can I not see out the results of find path? Anyone know? Oh, you worked at Chili's. That's fun. How was it working at Chili's? Why can I not do this? Why is this not compiling? C++ at this point, when we get here, hasn't even seen the function yet. Find path is void. Yes. You cannot print out the return value of find path because there isn't one. Right? You can't output a void because there's no value to output. So when you get find path here, if you were to change the name of that, it's like I've never heard of this person. Who is that? So when it gets here, all it's doing is just checking to make sure the types match up. L of data is in fact an int pointer. These are ints. It's not returning anything. Cool. Check. That's all it does. That's why you need to forward declare. Make sure I don't save that. That's all you need to do for C++ to be happy. So when you have a call to get image here, then it's just checking to make sure the types all match up, the return type matches up. Get image, we promised, would return a color grid pointer, which is again what we're talking about today. And that's a color grid pointer. Okay, everything's good. Neat. So that's all it needs when you forward declare something. Then down here is the actual code. C++ compiles the code from the top line to the bottom, which isn't necessarily a good thing. Yeah. In Java, you don't need to forward declare things, for example. It reads over your file first and then goes over it a second time. But C++ doesn't do that to save compilation speed. So you have to open the door for every customer and say, hi, welcome to Chili's. Huh. So you're the front, what was it called? The host, yeah. I was going to be like the greeter, but that's Walmart, right? Okay. So here is the read data function, and you'll see that it is taking in these pointer things. Okay. This is not how I would code. I would code this using call by reference, but this is essentially the C way of doing what we've been doing in C++ using call by reference. This is how it's called call by pointer, and it works pretty much exactly the same way as call by reference. So we're passing in width, height, and max value by reference essentially, and we're going to return an int pointer, and the int pointer being returned here is the array of data. So we open up a file. This is all done for you, by the way. You don't have to write this. So none of this code, I don't think you need to mess with any of this. This is actually just done for you. But it's probably worth looking at so you can understand it. So I'm just going to go through it real fast. So it's going to open up a file using ifstream, which you understand now as of 2 classes ago. So it's going to open up. Really, that's interesting that they do that. You don't need to do that. You can just do that. That's fine. Yeah. Huh. Then it's going to read the width and the height from the file. Remember, the first 2 numbers are the dimensions of the file that you're going to read. It reads those. It sets width equal to W. It sets height equal to H. This is basically call by reference, essentially. The syntax looks a little bit different, but it's doing call by reference. So width and height are having their values changed. It then allocates an array of size width times height. So this is creating a 2D array. So if it's 100 by 100, it's going to allocate 10,000 integers right here. And we'll talk about new and delete on Friday. It's a topic for another time. But basically what it's doing, it's making 10,000 integers all at once. And it's storing the result into a pointer. A pointer is just a memory address. It's the beginning of the chunk of memory here. So that's going to allocate 10,000 integers, or whatever width times height is. I'm just using 100 times 100 as an example. So it's going to allocate 10,000 integers, a big chunk of memory. That's 40,000 bytes, 40K of RAM, which is extraordinarily huge by today's standards, right? 40K of RAM, man, it's $40,000 of RAM, right? To hold 40K. Back in the day, that's how much it cost. Each K was $1,000, like back in the day, like in the 1980s. Yeah. So yeah, really, there was an explosion in RAM density that allowed RAM to go from being like you had to think like real carefully, like, do I want to buy the 4K version of this computer or the 8K version of the computer? Because you're talking about a $5,000 computer versus a $9,000 computer. Like, you think your 3090s were expensive? Think about how expensive 4K of RAM was back then. That's more expensive than a 3090 is even at scalped prices. You know, and that's in $1980, not in modern dollars. So RAM was stupid expensive. So if you ever wonder why C++ does some things, remember it came from that era when RAM was very limited. Okay. So anyway, so this pointer here is holding the start of that 40K block of RAM. That's the memory address for the start of that 40K block of RAM. I then added an assert here just to make sure that it worked. When you allocate memory, it's good practice to just make sure that it actually allocated. You didn't run out of RAM. It then runs through the entire file, and it reads in one elevation point at a time. And if it ever finds a higher elevation than the max that we've seen before, the max becomes the highest elevation. I didn't write this code, but you can see the ternary operator is used by real people in real life. And then it just reads into the array. So for int I equals 0, I is less than size, I plus plus, L of data, square bracket I equals val. So it's going to start at the beginning of the array, go to the end, and just read all of these values in. And that's it. Then it returns the array. So it's going to create an array of size 10,000. It fills it with the 10,000 elements from the file. That's how you read from a file, right? And then it returns the array. So this is very, very common code. And the reason why we're doing this assignment is so you guys get a little bit of practice working with files, working with 2D arrays, working with pointers, which is the topic for this chapter. So, yeah. Yeah, or floppy drives. You know how expensive a floppy drive was? Oh, Lord. Oh. Is there a README? Yeah, there's a README. It tells you everything you need to know. You don't have to memorize it. I'm just kind of giving you a high-level overview of what's in the code base already and what you need to do. So floppy drives back in the day were $800. In $1980, so it's like $1,600 today, something like that. Yeah, and so Steve Wozniak, who was one of the founders of Apple Computer with Steve Jobs, much less well known than Steve Jobs, but should be more well known than Steve Jobs because dude was like and still is, like, he's still alive. You know, I had some of my students meet him. Actually, they broke into his locker room or dressing room, technically. Anyway, so. He was given the challenge of making a cheap floppy drive because floppy drives are stupid expensive. And they wanted to have a floppy drive on the Apple II. And they really wanted to have two of them so you'd have your operating system disk in one and like your game disk in the other and not have to switch back and forth between them. And so he figured out a way of cutting the cost in half. And they motivated him to do that by saying, if you can make a cheaper floppy drive, we'll send you to Vegas for a week. And he was like, done. And so he like put down his genius brain on the table and just went bam and figured out a way of using software to control the floppy drive so that it got rid of the need for this expensive hardware controller and cut the cost in half, essentially. And made that's one of the reasons why the Apple II was a success, was because they got the cost low enough that even normal people could buy one. How many floppy drives are you getting? Yeah, if you were a boss, you would have two. You know, I did use one floppy drive systems. They're not fun. Okay, so what this is doing here is this is going to take the data This is the data that we had earlier, that we read from disk, right? And you pass in the width and the height, because remember, when you're working with an array, if all we had was that, would we know how big it was? If all we're passing in is the starting point of 40K of memory, do we know where the ending point is? And do we know how many rows there are and how many columns there are? If all we passed in was the pointer. No. And that's why I prefer vectors, because vectors carry their size information with them, right? So you can just query a vector and be like, hey, yo, how big are you? And it'll tell you. With a pointer, all it is a memory address. It's a spot in RAM. It's like, that's where the beginning of the array is. Okay, where's the ending? I don't know. Well, how am I not going to go out of bounds? Good luck. That's the C way of doing things. Good luck. Hope you don't screw up. Hope you don't get hacked. So why aren't you using vectors for this assignment? You can. You are absolutely 100% within your power able to rip out all of the pointer stuff and put vectors in instead. I'm explaining what the pointers are doing, so you can either choose to use them or you can choose to rip it out. Either way works. Either way, you have to understand them. Because this is how, like I said, arrays and pointers are used everywhere in the real world. And what's the difference between a pointer and an array? Nothing. They're the same thing. This code here could have been written like that. It compiles the same way. See that? No compile error. Same thing. Okay. Just passing an array of integers. When you pass an array of integers, what it passes in is the address of the first element, the beginning of the chunk of memory. And you just have to hope that these numbers here are right. Okay. And then it passes in the maximum value. Then it's going to iterate over the 2D array. And what it's going to do here is if the elevation is -1, remember that's how we, like when you do the find path function, which is the next one we're going to talk about, that takes place before this one. When you do find path, as you travel around the map, you're going to set the elevation to -1. You're going to carve a hole in the mountains. And so wherever there is a hole in the mountains, wherever the elevation is -1, then it's going to print out purple currently. You need to change it to blue. And if it's not the current path, then it outputs some sort of grayscale value from black to white. So how does color work? We use in this class a fairly standard coloring scheme. Pretty much all the assignments we're going to do with color in this class use this scheme. And it's called RGB, red, green, blue. Every color on the screen you see right here has a certain red value, green value, and blue value. And we're doing what's called 8-bit color. So there are 8 bits of red, 8 bits of green, 8 bits of blue. If you do HDR, you might get 10 bits of color. But not for this assignment. So this is 8-bit color. So the value, this is red, this is how much red there is, ranges from 0, which means no red, to 255, which means 100% red. So we're passing in, for this pixel that we're going to draw, 100% red, 0% green, 100% blue. Purple. Okay? And what you have to do for this assignment is figure out some way of changing it from purple to blue. And I'm not going to tell you how to do that. You guys think you can figure this out? Going from 100% red to 0% red? I don't know. It's pretty tricky. So, yeah, don't pass in a value over 255 either. I think it'll crash or something. Okay, so yeah, so you need to change this from purple to blue. That's one of the things you have to do. In this assignment, everything that you have to do is marked with U. So you and your partner can just search for U. / is search, right? Type in U. And then hit N a bunch of times, and it will show you all the places where you need to write code. Okay. So yeah, that's where we were. So you're going to need to change this from purple to blue. Okay. The rest of it's all functional. Okay. So for the read data, you don't need to mess with it. For get image, you only need to change the path color from purple to blue. And again, I'm not going to give you the answer, but it's pretty tricky. One number needs to change. Okay. And then find path. This is the heart of the program. This is the thing that you are going to have to spend the most time on. And you're going to have to understand how 2D arrays are held in 1D arrays for this to work. And that's where we're going to switch. When I switch over to coding, that's the main learning point for today. So this code here, find path, takes in the array of data, takes in how wide it is, how tall it is, the row that the player is going to start on. We're going to start on row 100. We always start on column 0. You always start on the left side of the map, and you travel to the right side of the map. So column starts at 0, and then until it hits the right edge of the map, column plus plus, so it's going to always go to the right. And I pulled it in 1 off the edge so that you don't need to worry about bounds checking the left and right edges. It'll stop 1 pixel away from the right edge. You can't tell, but I don't go to the very end because then you'll go off the edge. So I just pulled it in 1 notch. Or maybe they did. I don't know. I don't remember who wrote that. So what do we do with a drunken sailor? Here. This algebra here is the key to the assignment, and I'll explain what that means in just a little bit. So what you're going to do is your code here is like going to get the current elevation, and elevation is equal to something. Okay, you're going to get the current elevation. You're going to get the elevation of the person to the spot to the northeast. You're going to get the elevation of the spot to the east, and you're going to get the elevation of the spot to the southeast. And you're going to see which of these 3 values, northeast, east, and southeast, has the closest elevation to your current one. And if east is the closest in elevation, you do nothing. The row stays the same. If northeast elevation is the closest, you do row minus minus. If southeast elevation is the closest, row plus plus. And just make sure you don't go off the edge. And that's the thing. The something is the part that's going to explode your brain a little bit. And so I'm going to switch over and talk about the theory behind how the hell do you hold a 2D array in a 1D array. Okay. So here is a 2D array. This is a 5 by 5 array. There's 5 rows, 5 columns. So there's rows is equal to 5, columns is equal to 5. We've got 25 elements total. This is how they're indexed. If you have a 2D array, index 0, like this thing is held in a 1D array, right? So we visualize it in our brain as a 2D array, but actually on the computer in this assignment, it's held as a 1D array. So element 0 is the top left corner. Element 1 is 1 to the right. Element 2 is 1 to the right. Element 3 is 1 to the right. 4 to the right. And then when you go to 5, you've hit the end of the row. So you come down, the row goes up by 1. The column goes back to 0. And so this is element 5, element 6, element 7, element 8, element 9. Okay. So the map, you can think of this as like a mapping between 2D and 1D. Okay. So element 0 is this one. Element 1 is this one. Okay. And so there's an algebraic formula for figuring out, given a row and a column, what spot is that in the array. Okay. So if we are at row 1, column 2, if we're trying to get 7 here, this is row 1, column 2, right? 0, 1, 2, 0, 1. Okay. How do I get 7? Well, the size of the array is 5. So watch this. Every time you go down a row, do you see that? The index goes up by 5. Every time you go up a row, the index goes down by 5. So 7 minus 5 is 2, right? You don't understand why you're using a 1D array instead of a 2D array? Because passing a 2D array to a function is stupid. It's what it amounts to. You have to hard code the size of the array into the function parameter itself. And so you'd have to make a separate function for every possible size array that you want to pass in. And nobody wants to do that. So this is just how it's done. Also, you might be like, all right, let's use a vector of vectors. That's fine. And that's what I did when I solved this assignment. I took this code and refactored it and made it a vector of vectors. However, vector of vectors is slower than this. This is how things are done in the high-performance computing world. I write code, like when I'm writing high-performance code, this is how I do it. I hold everything in a 1D array. It's the fastest way of doing it. A vector of vectors is fine for... Got cats fighting outside again. A vector of vectors is fine for casuals, for filthy casuals. It's fine for vector vectors. But if you want the fastest possible speed, you do this, basically. Like I said, speed is not something that you should concern yourself with necessarily in this class. Okay, so, yeah, lightsaber cats, exactly. So, do you guys see, like, intuition, like, if we were currently here, if we were currently at spot 7, and we wanted to move north, do you see how we're moving columns left? Right? Because there's 1, 2, 3, 4, 5 columns. So if you subtract 5, it goes up a row. Because it's like reading a book, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 15. And so every 5 columns is 1 row down, right? So computer science is a lot of pattern matching and problem solving and just staring at numbers and being like, okay, so what does it mean to go up a row? What does it mean to go right a spot? You know what I mean? Like, how do the numbers change? Like, if I'm currently at 7, what is the index of the person east of me? Row minus 1 is minus 5. It's minus the number of columns. So what about going east? If I want to travel east, what is the index of the person east of me? Yeah. So traveling east is just plus 1. I don't know if there's a better way I can write this. So traveling east is just, you just add 1 to the index. So you've got this big 1D array. If I'm at address 3, if I go to address 4, that's 1 to the right. Like that. See that? If I'm at 0, 1 to the right is 2. Okay, so east is just plus 1 until you hit the edge of the map and then you wrap around and bounce checking and stuff like that. Okay, so if I want to travel northeast, how do I do that? What's the algebra for traveling northeast? I'm going, my row is decreasing by 1 and my column is increasing by 1. So what is that? Yeah, you make 1 step north. North is equal to a minus 5, right? So you just do both of these. Right? So north is minus 5, south is plus 5. And west is what? What is west? We don't go west, though, so we don't care. We're only traveling east, northeast, and southeast. And so if we wanted to travel northeast, it would be minus 4. And if we want to travel southeast, it's plus 6. Right? Because east is plus 1, north is minus 5. And if you wanted to be more precise here, where did that 5 come from? Why is it 5? Why is subtracting 5 causing it to go north 1? What does that mean? Is that going to work on your assignment if you subtract 5? No, it won't. It's the size of a row. Yeah, the size of a row, which is to say the number of columns. So if you subtract columns, you go north 1. And if you add columns, you go south 1. And then east is always just 1 to the right. So northeast is going to be, you subtract how many columns you have plus 1. right? So subtract 5 plus 1, and that's a northeast move. This is the assignment. This is the assignment. You work this out. You got it. Because the rest of the logic's actually pretty easy. So if I were to ask you which spot in the 2D array corresponds to row, let's see, to row 3, column 4. What index is this? This is a 2D coordinate. What is its index in 1D world, in the 1D array? If it's row 3, column 4, what is that in the 1D array? So row 0, 1, 2, 3. So this is row 3 here. Column 4, 0, 1, 2, 3, 4. It's index 19. Row 0, 1, 2, 3. So every time you go down a row, how much does our index go up? 5, right? And so the algebra for this, it's going to be the row times the size of a row plus the column. Algebra. See that? You go down a row, it's plus 5, plus 5, plus 5. Every time you go right a column, it's plus 1, plus 1, plus 1. So that is how we got 19 out of that. Seems easy? Good, because I actually give you the algebra right here. So the row that you want to access times the size of a row, which is the width of the image. That's the width of a row. So which row every time you go down, like if it's 100 by 100, every time you go down one, you're going 100 plus 100, right? So it's the row you're on times the width of a row plus the column. That's the algebra right there. And you're going to use that to pull the, you're going to pull your current elevation out. It's like, let's say we're at 7 right now. You'd pull the current elevation out. You'd use the algebra to get that number. You get your current elevation. You get the elevation of the person to your right, which is plus 1. The elevation of the person northeast of you, which is minus 4. The elevation of the person southeast of you, which is plus 6. And again, these numbers come from the fact moving north is minus 5, moving south is plus 5, and moving east is plus 1. So minus 5 plus 1 is minus 4. Plus 5 plus 1 is 6. Plus 6. So you're going to grab these, you're going to get these 4 numbers out of the 1D array, and then you're going to see which one of these 3 is the closest. Is east the closest to elevation? Is northeast the closest? Or southeast the closest? And then you just adjust the row correspondingly and repeat until the end. That's it. That's the whole assignment. You have a week to work on it. You can have 1 or 2 partners. Go ahead and post on to the chat channel now if you want to partner on the assignment. That's it. Okay. This is something. This concept is called row major ordering, by the way. Can you go solo? Yeah. Sure. Back in the day, I would like partner people up, but on Discord it's just too annoying to, like if you ghost somebody, like there's not a whole lot you can do about it when you're on Discord, you know what I mean? Like, bro, let's work on this. Crickets. At least in real life, like the person sitting next to you, you're like, let's work on it. They can't like ignore you, like they're sitting next to you, So. It's one of the downsides to online learning is you don't have that same peer pressure. Come on, let's work on it. Okay, fine. It's lab time. I guess I have to be here. Pardon me, please. Hard time finding work because of schedules. On the flip side, we go back in person next semester. Yeah. So news on that. The current plan is there will be 1 section of online 41. So if you are one of the people who live further away from campus, you're more than welcome to take second semester computer science online. I'll be teaching 1 online section of 41 and 1 in-person section of 41. So you can either take it in person or you can take it online. It's your choice. I think we're going to have an online session of 40, just in case you fail. And there's going to be an online session of 26 as well. So online it's better than in person because gas isn't cheap. Yeah, like there's a lot of people that like live in Reedley and stuff like that, or up in Oakhurst. I actually have quite a few students from Oakhurst, and that's it's a drive. The 41 kind of sucks, It kind of just does. I don't know. Like, I heard that they were supposed to have like improved the 41 between Fresno and Oakhurst a while back, and somebody like misappropriated the money or something. Like it was supposed to be like a real interstate kind of thing, and like the money got stolen or something. I don't know. So 25-minute drive, $4 a gallon. Yeah. Just download more gas, Hazelton. Yeah. I like visiting Oakhurst, but like I really wish somebody would just come in with a bulldozer and just widen out those things and make it 3 lanes wide all the way up to Yosemite. Okay, so let's talk about pointers. So a pointer is something you're going to see all the time, like this. And what this means here is it just means it's an array. Use it the same way. So it doesn't matter. You see how the code compiles either way. And down here, I don't know, I guess I'm not using it, but you do L of data 10. And even though it's a pointer, you can access it like it's an array. Because it is. Pointers are arrays are pointers. Again, for you pedantic people, there is a very small difference. Yes, I know. Okay, so we're going to go over like the syntax of pointers first. And all this kind of stuff here is kind of stupid. Not the first 3 lines here. Let me comment these out and I'll talk about them in a little bit. But I'm just going to show you guys what there's a couple operators in C++ we haven't seen until now. I'm just going to explain what they are and what they do, even though you're never going to write code this way. More people would go to Yosemite, yeah, they would. And it'd probably be good for Oakhurst, with more tourism coming in and stuff. So, although, more pollution too, and stuff like that. Okay, so here I've got a integer named x whose value is 42. Remember, every variable is a combination of 4 things. The name of the variable, x, the type, int, the value, 42, and the thing that we never talk about, except once earlier in the semester, the memory address. Somewhere within RAM, somewhere within the 32 gigabytes of RAM you have inside of your computer, somewhere inside of there, a value is being set to 42. And normally we don't care about that. But if we want to care about it, we can do so. And we can do so like this, using the ampersand. So the ampersand operator gives you the address of a variable. And normally we don't care about this. But if we want to store it, we can store it into something called a pointer. Pointers are just integers, really. They're just an integer. But they very specifically will only hold memory addresses. And very specifically, even more very specifically, an int pointer will only hold the memory address of an integer. So we're making a variable here named pointer. It's of type int pointer. So it only holds memory addresses of ints. And whose memory address is it holding? X. So if you were to print out the memory address of x, or if you printed out pointer, you're going to get the same value, because pointer holds the memory address of x. And if you print out the value of x, you'll get 42. And if you print out this, which is the other operator, it's the opposite of the ampersand, it tells you, give me the variable at that memory address. This will print out 42 also. So you have the at operator, the ampersand operator, that tells you the memory address of the variable. And then you have the dereference operator, which looks like multiply, but it's not. This is a unary, it's the unary star operator. It's the dereference operator. What that says is, give me the value at this location in RAM. So pointer holds some location in RAM, 7FFFFFF, something, 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 some address in RAM. And it's saying, hey, tell me what's stored there. And that's why you need to know that you're an int pointer, because when you read those bits out, you need to know, are you a double? Are you an int? Are you a char? What are you? And so what this is doing here is this is saying it's going to read those zeros and ones and say, oh, that's the number 42. Then it prints it to the screen. And so if we were to run this, you'll see that the memory address of x is 7FFF something, something, something. The value of x is 42. The pointer is the same. See? Same memory address. And the value held at that memory address is 42. Same thing. It's two different ways of accessing the same variable, in fact. So if we change the value of x, if we did x++ like that, then when we print out the value at the RAM there, it's going to be 43. Like that. So we print out 42, we update the value to be 43, and then we say, hey, give us what's at that RAM address. Well, it's 43 now. Or we could do the same thing using a pointer. So if we dereference the pointer, dereferencing the pointer like that is exactly the same thing as if I'd written x there. Because the ampersand operator and the star operator are opposites. And so if you dereference the reference, they cancel each other out. So pointer is holding the reference of x, and that is dereferencing that reference. So this is as if I'd written x. Okay. Again, there's absolutely no point to doing this. You would not write code this way. This is just to demonstrate how the operators work. So if I do this, this will also print 43. Just a different way of accessing x. All right. So here we are setting pointer equal to the address of y. So pointer already exists. Notice how there's no star here, right? Because what is the type of PTR? The type of it is int star. Okay. And where the star goes, actually, I usually write it like that, actually, instead. But some students in the previous class were like, well, why do you not need the star down here? It's because the type of it is actually int star. But you could write it like this if you hated your fellow man. So, okay. Yeah. So do you guys see what's happening here? So now this variable that only holds RAM addresses events, this variable is now holding the RAM address of y instead of x. See that? So what is it going to print out when we print out the value held at that RAM address? Can you even see? What's the value of y? Yeah, it'll print out 420. So pointers can be used to point at different things if you want. Again, there's no reason why you do this. If you want to see something really horrible, watch this. Remember how I said arrays are pointers and pointers are arrays? Pointer is pointing at a single. Pointer is pointing at a single variable. So this is going to point at. Pointer is pointing at y, and so if I say pointer square bracket 1, that says give me the variable after y in memory. And I have no idea what's there. It's probably going to be z or something, I don't know. So this is just going to randomly print out something garbage. Yeah, negative, you know, whatever. It's whatever was in RAM there. But if I said pointer 0, the first element in the array there, hey, look, I got 420. See that? Because arrays are pointers and pointers are arrays. So you say, give me the first element in the array. Well, that's just y, because it's pointing at y. And if you want to see something really horrible, let's just delete that entirely. And pointer is now pointing at X, right? So if I say giving the person in RAM after X, well, that could have been Y. It was last time I ran it. It wasn't this time. Oh well. Okay. It could be. It could be 420. It could not be. And this is just garbage code, and you should never, ever do it. Okay, so int star pointer equals the address of Y. Oh. Some people call it putter. Putter equals the address of Y. Pointers like the start of an array. Yeah, they point. When you have an array, the pointer just points at the start of the array. And if it's pointing at a variable, it's exactly the same thing. It's an array of length 1, essentially. There's really no difference between a variable and just a very, very small array, right? You can see, like, they just kind of work the same way. Because a pointer is just the start of the array. And that's why you need to have length information. Anytime you pass a pointer to a function, you need to say how big the array is. Otherwise, you don't know where the end is. Okay. So here we have something that's a little bit more useful. And, oh yeah, one more point on the syntax. We made here a double Z, and then we tried having a pointer point at it, an int pointer point at it, and it doesn't work. And the reason for that is because int pointers only hold pointers to ints. They do not hold a pointer to doubles. It's an incompatible type. So if you want to have a pointer pointing at a double, you have to have a double pointer. You can't use an int pointer. Now, let's talk about something useful. This is just to sort of introduce the syntax to you a little bit. Last time it worked, yeah, Mincorelli can confirm that worked in the previous class. It just is like, don't do that. You know, like, don't rely on variables being next to each other in RAM. Like, there's maybe somebody with a better understanding than me would, but just don't do that. Just don't do it. It's terrible. Okay, so here we have a function that takes a pointer. That's the start of a big block of RAM. And it's going to take in a number of rows and a number of columns. And so here, let's uncomment you. It's going to be 10 by 10. And let's do it a little more properly. Maybe const size t rows is equal to, we'll do 3 rows and 6 columns. Okay. When you use curly braces to initialize an array, it'll initialize them starting at 0, 0, and then going to the right. It's kind of like reading a book, right? It fills it in just in the 1D sense of the word. And then the rest of them are initialized to 0. So that's actually kind of nice. So the first 5 elements are going to be 10, 20, 30, 40, 50. Then all the other elements after that are set to 0. Yay, I don't have to write a for loop to initialize everything. That's cool. And then I'm passing array here to print array. And I'm giving it the dimensions. How many rows, how many columns. And so this for loop should look fairly familiar to you for those of you that did the times table assignment, which hopefully is all of you at this point. So it is going to, remember the algebra that we talked about? It's going to output an element in the 2D array, which is a 1D array, followed by a tab, and then when it gets to the end of a row, it prints out a new line. And this will print out a 2D grid of numbers. And this, again, this is the heart of your homework assignment. To access a 1D, to convert from a 2D coordinate with a row and a column to a 1D array, the row you're on times the size of a row plus the column. That's the algebra. That's what you have to do for the homework assignment. Okay. And there you go. So you can see 10, 20, 30, 40, 50, and then everything else is initialized to 0. There you go. That's pointers. Very, very commonly used in the real world. If you want, you can refactor all this to use a doubly nested vector thingy. Or you can learn to work with pointers either way. It's probably good for your computer science knowledge to work on it, because this is the next topic. Our next topic is pointers. So it's good practice, even if you don't use them very much. Okay. Make this a const. We can't change it by accident. So if I now tried saying array 0 is equal to 42, it's going to yell at me. So, passing something by constant pointer is very similar to constant reference. In fact, underneath the hood, it's exactly the same. Passing something by pointer is the same thing as passing a reference, like a call by reference parameter. When you're passing something by reference, all you're doing is passing the memory address. You pass the memory address under the hood. It hides the fact that you're passing memory address. It looks like just a regular variable. You know, like if we wanted to pass this in by reference, you can still use the variable the same way here. You know, it just looks like a regular variable. But what's happening is that it's actually passing a pointer. It passes a pointer kind of under the hood, but hides that fact from you. You just use rows like a regular variable. Okay. Now there's no reason to pass these things by reference because they're primitives. Primitives are probably slower to pass by reference than by value, but demonstrates the point. Okay. Or you could pass in a pointer or something. Yeah. So there you go. That's class. Do you guys have any questions about it? We're in a CSI 41 looks ominously in the distance, waiting for 40 students to learn pointers. Yeah, pointers are actually really useful in CSI 41. In CSI 40, the uses of pointers are a little bit more contrived. If you're working with C-style code, like for this assignment, yeah, pointers are used everywhere. They just use them instead of call by reference, like we saw. They didn't have any call by reference parameters. They used call by pointer instead. Same code. Under the assembly, if you look at it, is going to be basically the same. It's just whether or not you're consciously aware that you're passing in a memory address or not. It's the only difference. Okay. Any questions about this? Memory management. Yeah. On Friday, we'll talk about new and delete, which is also going to be very useful for 41. Call by pointer and call by reference are pretty much interchangeable. Yes, they're like again. If you look at the assembly output, I can't say that for sure because who knows. But basically, call by pointer and call by reference should actually even compile to the same assembly code. It's just a matter of syntax, whether or not you want rows here to act like a regular variable, like this. If you were to pass this in call by pointer, like that, then you would have to do that. You'd have to dereference it every time. And when you pass it down here, you pass the address, like that. So that's where call by reference came from. Rather than having to do this every time you pass something by reference, they just put it up here in the function. So this code here, where we're passing rows by pointer, is exactly the same as calls being passed by reference. It's just the syntax. You have to dereference this every time. It's kind of annoying. I kind of prefer call by reference, but if you the call by reference does not work in C. So if you work with C people, Linux system calls, for example, if you want to make a Linux system call, they're all pointers. There's no references in any Linux system call. You can't pass a reference. You have to pass a pointer. So, you got to know, even though you're not going to code it that often. Okay. All right, so I'll put this demo code up so you can gaze at it at your leisure. Main.cc. It does have the answer to the homework assignment in it. I'll call this pointer demo.cc. And if you guys want a copy of it, it will be up right now. Contains the homework solution. There you go. And hopefully the people in the other class will see that. The homework solution is that. That's how you convert from row and column to a 1D coordinate. That right there. Okay. So I'll see you guys on Friday. We're going to learn about new and delete on Friday and maybe give you some lab time to work on the homework assignment. Did you pin it? Oh, yeah. Yeah. Pinged the class on that. Cool. All right. So I'll see you guys on Friday. Peace out.